Okay, so to start with, these first two examples that we have are just, again, reminders to you of what the question is asking, / how do we find all of our zeros. Okay, this one has two different questions, and I love that these are side by side because people will sometimes confuse these questions for each other. When it says possible, that doesn't mean the actual. When it says possible rational zeros, that's the question that's asking you to list your P over Qs. Right? So factors of 4 over factors of 1. That's your possible rational zeros. Then it says when it says identify our actual zeros, that's when we go find the ones that work. Okay? Now you are welcome to have a calculator to support you today as we're going through these. Understand that some of these that are a little bit lower end computation ones are definitely fair game for a non-calculator quiz. We have lots of options of how we can find a zero that works. We are currently looking at an x cubed that is not factorable. So I have to find at least one zero that works to work this down to an x squared. Once it's down to an x squared, I don't have to keep trying. I can just stop and factor, right? So let's go ahead and grab our calculators, find me a zero that works, please. And you don't even need a calculator. You can just do this on your paper in synthetic division as well. You said 1 works. And again, we can just plug them in and look for a 0, synthetic division, and get a remainder of 0. So on my list of zeros, 1 works. Finding the rest of my zeros, I would stop, write out my quadratic, because otherwise it's just guessing and checking and not guaranteed to find any more, and try to factor. Well, what are the factors of -4 that add up to -2? There aren't any. 1 and 4 will never add up to 2. 2 and 2 can't add up to 2. So I have to go to my quadratic formula. So -b plus or minus b squared minus 4 times a times c. Reminder, as we are doing this all over 2a, we will never get decimals. Okay, we're not ever going to round a decimal on this, is that we are going to find these exactly, simplifying our radicals as we go. So 4 plus 16 would be 20. Finding my perfect squares that go into 20, 4 times 5 is 20. So that'd be 2 square root of 5. And as always, simplifying our outside numbers on this. 2, 2, and 2 are all divisible by 2. So we'd end up with 1 plus or minus 1 square root of 5 over 1, which actually can just look like 1 plus or minus square root of 5. Okay. Now, some people confuse the whole complex numbers with numbers that have square roots in them, like a quadratic. Although this one simplified and separated itself into 2 terms, you don't have to break those because they're not imaginary and real. I mean, that's also a real number. It's an ugly number, but it's real. But if you break everything into the 2 numbers, you'll never be wrong. Okay, so that's always an option, like you did on your assignment last night, breaking things into real and imaginary. Okay? All right, next one. Same directions. List the possible, find the zeros. Okay, I'll give you a second to work ahead of me on this one. Very short list of numbers we can try out on this one, right? Plus or minus 1. So it has to be one of those or we can't factor this. So not a lot to check out here, but you have to realize that we were missing a term. If you did not fill in the 0x squared, we're going to be, our synthetic division will not work out here for our 0. So 1, 0, negative 2, negative 1. Negative 1? 1?
No, negative 1.
Okay. And then we're back to where we were on the last one. The only thing you see on this one is that it doesn't break, so we get x squared minus x minus 1. Again, not factorable. There are no factors of negative 1 that will add up to negative 1. Okay, so that means I have to go to my quadratic formula. And the difference you'll notice on this one is as we simplify, so 1 plus 4 is 5. There's not a lot of simplifying to do. And I just want to clarify. You can absolutely 100% leave it as 1 plus or minus square root of 5 over 2. Yesterday we practiced breaking something that looked like that, but we broke it because the second one was imaginary. This is not imaginary, so you don't have to break it, but you can if you want to. So you can write that, or you can write 1/2 plus or minus square root of 5 over 2 because you would break it and give them both that common denominator. Totally up to you. Or just write that. Questions?
So it's not 1, it's negative 1 because usually when you do that, it's like x minus 1 and then you set it to 0.
Right. Right. So that's the difference between like factors and zeros. The number that is out front of your synthetic division is the 0. Other questions? All right. Last one where we're just kind of doing that today will be this one. Again, I see that it's an x to the 4th. Now, all I'm going to ask you to do on this one, use your plus or minus p over q's to find me 1. I only want one factor, and please stop after you get that 1. Do synthetic division one time and stop. What? I want 1, 0 for this one, but I don't want us to move any farther past that. There is another one, but I want us to find 1, 0 of this one and stop, please. Again, we've got options. If this is a graphing calculator part, which it absolutely could be, I would totally speed up my process and type that in and look at my table because it'll check a whole bunch of them for me really fast. What is one that works in this one? 2. Okay, let's see here. 2 works, okay? Now this is the reason I said find 1 and stop. There is another one that you would be able to find, but I also want you guys to be good algebra students and pause here. When you get to 4 terms and x cubed, guys, look and see if it's factorable by grouping, okay? And again, what am I looking for? Is if I were to take out the GCF here and take out the GCF here, would it match? And can you see that it would? If I took out a 3 here, that it would be 1 and 5, just like this one is 1 and 5. And when you see that, stop and factor it. Because again, factoring is going to be faster and more efficient. So I would stop here and call this x cubed plus 5x squared plus 3x plus 15. Group my first 2, group my last 2, take out my GCF. And what's left over should match. Take out what matches and make a parentheses for what's left over. Okay. Now, if I had continued to guess and check, I would have eventually found that -5 was another 0 that would work, and we could have worked this down to the quadratic. The quadratic we would have had left over was x squared plus 3. Finding our zeros, again, anything that has an x gets set equal to 0. And solve. The thing that is so commonly forgotten on this is the original. Don't forget that guy. So I always say when you get it, immediately write on the answer line, 2 worked, okay? -5 is another one. And today it's asking us for all of our zeros. We've seen this over and over and over again. We went to solve it and we said, uh-oh, I'm square rooting a negative, that's imaginary. Well, we don't throw out imaginaries anymore, right? But we have to remember that when I insert the square root, I also have to insert a plus or minus every time, okay? So simplify your square root like normal. Square root of 3 is not going to simplify, but the negative comes out as an I. So plus or minus I square root of 3 is your last two zeros. Okay, now we're going to stick with this problem here for a minute, but do we have any questions up to this point? On your assignment today, you're going to look at a problem just like this, and it's going to have two different types of directions, and I want to just very clearly go through those two different types of directions with you so you know exactly what it's asking, because the wording is a little bit tricky. It's a vocab we haven't used. This is the exact problem we just did. Those were the 4 zeros we got. -5, +2, plus or minus I squared of 3. Those should all look familiar. They're on your paper still, right? The two different directions are this. List the function as a product of linear and then it's this phrase that I didn't think we would know. Irreducible quadratic factors. Now when they say the word factors, I know my answer is going to look like parentheses, right? The first two are easy to do. I use the opposite sign. A 0 of -5 looks like x plus 5. A 0 of +2 looks like x minus 2. It's this whole irreducible quadratic, and when we run into that thing, that we run into an issue. And an irreducible quadratic, what we have always called it is not factorable. When we run into a quadratic that is not factorable, it's an irreducible quadratic. So going back over the last couple pages, this, not factorable, right? This, not factorable. Every time we've stopped and said not factorable, the fancy math word they use is irreducible quadratic. So if we were supposed to put this into that question, we would say, what was our other 0? -1. So x plus 1 times that, because it's an irreducible quadratic. So let's go back and finish out the problem we were just doing. This in the irreducible quadratic was x squared plus 3. It's at that moment when we stop and say something is not factorable and it's an x squared. That's that point. Now, I don't love that that's part of the directions in this one because I don't assess you over that. I assess you over this next one. Okay, so this of those two directions is the one I want you to understand better. Linear factors. And x squared is not linear. Okay, so that would not be counted as a linear factor. A linear factor is doing it just like we see these things, and it just looks weird when it's something like a radical or an imaginary. But x plus 5 is linear, x minus 2 is linear, and then we just use these the same way we were doing the other ones. So x plus I square root of 3 and x minus I square root of 3. I just want you to look at those two different directions because the phrase irreducible quadratic throws people off. Your assessment, your test next week will ask you to write them as linear. Okay? Questions? All right. This one is something that we've actually already talked about. This is straight out of your book, and I know it gets a little bit, so I'm going to highlight what I want you to get out of this. Over the last, I don't know, couple of weeks, we have talked about this part of it, a polynomial function of degree n. Degree n meaning its biggest exponent. So whatever its biggest exponent is, it has exactly that many zeros. Haven't I said that a lot? That if it's an x cubed, that we have 3 zeros. If it's an x to the 4th, we have 4 zeros, right? And then they clarify that a little bit. That can happen from repeated zeros, multiplicities, right? Sometimes that accounts for a missing 0. That can happen from complex numbers, which is imaginaries. But through all of that, your total number of zeros that you have on that 0 line should match your biggest exponent. And if it doesn't, something went wrong, right? So that's kind of what we're looking for on this next part. And the whole complex number thing, the other thing I want to point on that is that imaginary numbers always, always, always come as a pair. They will never come as a singular number, ever. So I say they come with their imaginary friend. You will only ever be told one of them. If you are told that your polynomial has a 0 of 3i, it automatically has a 0 of negative 3i. If you think about where we've always gotten them from, it's when we were square rooting and had to put plus or minus, which is why there's 2 of them. Or it came from doing the quadratic formula, which has a built-in plus or minus, right? So doesn't it make sense that it always comes as a pair? But you'll only ever be told one because they feel like it's being redundant to tell you that the other one's there. Because if one's there, the other one has to be, because they come always as plus or minus. Okay, so let me show you one of the places that that will show up, and tomorrow we'll look at the other place that that will show up. One of those places is this. You guys have seen this question over and over. You have not seen it with an imaginary 0. So it says write a polynomial, which means at some point I'm going to be foiling, right? Because that's what polynomial means. Write a polynomial of least degree with real coefficients in standard form that has zeros of negative 1, 2, and this is what's new to us, 2i. And as soon as I see that on my list, also negative 2i is a 0, which will never be told to me. One of them will. Yes, the degree is 4. Because there are 4 zeros up there. One we just have to understand. Okay, we're going to get this set up. We'll clean it up a bit, and then we're going to go back and see how we can speed it up a little bit. So given zeros, start with factors. X minus, negative 1 would look like an x plus 1. A positive 2 would look like an x minus 2. And then your imaginaries, x minus 2i and x plus 2i. Okay, your imaginaries have to come as a pair here. And remember the directions say polynomial. So at this point, we're going to FOIL and FOIL and FOIL. I would always do the 2 imaginaries together. So do the other 2 together. So I'm going to FOIL this first pair. X squared minus 2x plus x would be minus x. And then this is what we practiced yesterday, right? Learning how to FOIL with imaginaries. Now, you might recognize the setup here, which we're going to come back and talk about in just a second. But if you don't, guess what? FOILing will still get you to the same answer. It'll just be more work. And that's OK. We get x squared plus 2ix minus 2ix minus 4i squared, which is actually minus 4 times negative 1, which is actually plus 4, right? All of that thought process that we went through yesterday. And then those middle terms, negative 2xi plus 2xi, cancel. Did anyone see that coming? Yeah, hopefully we did. Which leaves us with x squared plus 4. Yeah? Not done. FOIL one more time. Take each of these terms and distribute it through. So taking the x squared distributed through would give me x to the 4th plus 4x squared. Take the negative x through. Take the negative 2 through. Combine my like terms. And call it a day. Okay. Now I promised you that we were going to try to speed this up. So let's speed up our process here. When I am told I've got an imaginary 0, first of all, we practiced this a long time ago. When I was told I had an imaginary, I knew I could create a, whoa, that's not what we want. I knew that I could create an imaginary from going an x squared plus a number, right? You remember those conversations? Okay, so if they tell me specifically what that imaginary is, once I get this set up, let's skip over all of that FOIL and get straight to here. Can we do that? So let's talk about how to do that. Well, it's going to be an x squared plus. It's basically this part that I need to figure out. Where's that number coming from? Square the 2. Square the 2. So we're going to practice that. We're going to skip the whole FOIL thing. Let's practice that real quick. That's one of your zeros. Give me the factor it came from. X squared plus 49. Look how much time I just saved myself. Okay, now I show you that shortcut, and then I'm going to show you the one that's going to mess people up. That's one of your zeros. Slow down. What factor did that come from? X squared plus, because it's imaginary, Think how we got this one. We took this number and we squared it and it gave us that, right? So take this number. Yeah, square it. Square root of 5 squared is 5. Now, the answer I see there a lot is x squared plus 25. Do you see where people would get that? And that might have been going on in your brain. But understand when you got that square root that it's actually just going to be the number under the square root when you square it. Okay? So please feel free to use the shortcut to get to that. If you're uncomfortable with that, FOIL, it'll get you there. Okay? Your assignment tonight is out of the book. I am changing some directions. So those two that are highlighted in purple, 18 and 24, all you are doing is finding the zeros.
You don't know how to do
I don't.